Hello everyone. Let's analyze. So today we're going to talk about the arithmetic of function limits. In a previous lecture, we discussed the arithmetic of sequence limits. And now that we know that function limits and sequence limits are connected, we can actually derive the arithmetic of function limits by alluding to the arithmetic of sequence limits. So let's refer to the results of the last lecture, which is that the two statements in this theorem are equivalent. That a function has a limit at x naught is equivalent to saying that f of xn has a limit where xn is a sequence of elements in the domain, none equal to x naught, where the limit occurs. But xn converges to x naught. So let's explore computing arithmetic results of function limits by looking at it in terms of sequence limit. Suppose, for example, that f and g are functions from d to r, and that x naught is an accumulation point of d. Let's suppose that the limit as x approaches x naught of f is big F, and the limit of g at x naught is big G. In other words, f and g both satisfy statement 1. Right? Both are functions with the limit at x naught. So let's put our theorem to work. Let's suppose that the hypothesis of statement 2 is true. In other words, the sequence xn is in the domain, xn is not equal to x naught, and xn converges to x naught as n goes to infinity. Now, we know from the theorem that the limit as n approaches infinity of f of xn is f, and the limit as n approaches infinity of g of xn is g. Right? Because we know that for both f and g, statement 1 is true, therefore statement 2 has to be true. Now we have two convergent sequences. F of xn and g of xn are both sequences that converge. And from what we know about the arithmetic of sequences, the limit of the sum of those sequences, f of xn plus g of xn, converges to the sum of the limits, big F plus big G. Now, since xn was an arbitrary sequence, we know that statement 2 is true about the function f plus g. And because statement 2 is true about the function f plus g, then statement 1 has to be true about the function f plus g. So we've proven the sum result of function limits. So let's put it in the theorem. Suppose f and g map some domain A to R, where x naught is an accumulation point of the domain, and f and g have limits at x naught. In other words, right, what we just assumed in the previous slide. Then the function f plus g has a limit at x naught. In other words, I can distribute the limit so long as f and g each have limits. The same is true for products. If I take the limit of f times g, I get the limit of f times the limit of g. And the last, of course, for the quotient rule for function limits, so long as the denominator is never 0 and doesn't converge to 0, then we can distribute the limit to the numerator and denominator. So of course we've proven result 1. You'll prove result 2 in the homework, and result 3 follows, well, in the exact way as result 1 follows, so does result 2. The reasoning is precisely the same. So let's go back to our definition of a limit. We know that f has a limit at L at x naught if and only if x naught is an accumulation point of the domain, and for any epsilon, there's a delta, so that if x is in the domain of f and within delta of x naught but not equal to x naught, then the difference between f and L is less than epsilon. Now, hopefully it's clear in this picture that this function does not have a limit of L at x naught. The reason is, for the particular epsilon given, there is no delta, right, that'll give me f of x completely within this epsilon delta box. In other words, this f of x over here is further from L than epsilon. And no matter how small I make delta, that's always going to be true. Right? So for this epsilon, there is no delta for which this statement is true. Right? I can find an x arbitrarily close to x naught for which this difference, this bound, is untrue. However, every x that kind of breaks the rules is to the right of x naught. If I were to look only from the left, I might think, well, from the left I do approach L. It's only the right side that kind of ruins things. So what if I have x that satisfies all of these conditions so long as x is less than x naught? Well, in that case, I have a left limit. And you'll notice that a left limit has exactly the same definition as a limit, but with the extra criteria that x is less than x naught. In other words, our epsilon delta box is has a width that goes from x naught minus delta to x naught. Because if x is within delta of x naught and x is less than x naught, then that necessarily means that x is contained in the open interval from x naught minus delta to x naught. And if every x in this interval guarantees that f of x minus L is less than epsilon, then we say that my function has a left limit, or sometimes it's called a lower limit. Similarly, if I only consider x to the right of x naught, and any x to the right of x naught satisfies the definition of a limit, then I say that f has a right limit, L. Notice x has to satisfy all the criteria of a limit, but only when x is greater than x naught. And of course, if x is within delta of x naught, but not equal to x naught, and x is greater than x naught, then x must necessarily lie in the open interval x naught to x naught plus delta. So this interval here. So that's the definition of a right limit, right? We're really considering what happens as x approaches x naught from the right. So while this function here does not have a limit, it does have a left limit, and it does have a right limit. Now suppose that f has a limit L from the left and a limit R from the right. This superscript negative indicates a left limit. In other words, as x approaches x naught from the left. And the superscript positive indicates a right limit, or as x approaches x naught from the right. So suppose I have a function that has a left limit and has a right limit. Well, then L equals R if and only if my function has a limit of L. Because we can see in this picture that we have exactly the scenario of a standard limit, right? We have exactly our 2 delta by 2 epsilon box. And so long as x is within delta of x naught, we can see here that f of x from both sides is within epsilon of L. So if an overall limit exists, then the limit from the left and the right have to agree. And if the limit from the left and the right agree, then my overall limit exists. Well, that's it for today.